Hi guys, welcome to Vertical and Horizontal Asymptotes, Part 2. In this part, we're going to learn to manually calculate the limit as x goes to infinity for a function. Before we do it, I want to show you a really true way to do limits. Obviously, there are quicker ways. And we're going to look at a function. It's a rational function, and I want to evaluate the limit as x goes to infinity. I'm only going to do it from the right side. I'm going to skip doing it from the left side to save time. So what I'm evaluating is the limit as x goes to positive infinity. That means that I should let x take on larger and larger values because x is going to positive infinity. That might be a little hard to read, so I'll rewrite it over here. So as x gets increasingly large, we want to see what happens to y. So we begin with values for x. If x is 10, y is 1/10, which is 0.1. Let's just work out a bigger value for x. Say x is 100, and I'm just going to keep getting x to be bigger and bigger, and we're going to see what happens to the y values. If x is 1,000, you get 1 over 1,000, which is 0.001. So you can see what's happening is the y's are getting smaller. As x gets bigger and bigger, the y is getting smaller and smaller. In fact, if you made this an absolutely huge number, that number is, I think, 1 trillion. It has 9 zeros. That would be 1 over 1 trillion, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. That is one tiny number. The fact is that the bigger x gets, the smaller the y's get. And in fact, if you keep doing this, you're going to get very, very close, if not all the way to the number 0. And that's what we say the limit is as x goes to infinity. Were I to do it in the negative case, you would have the exact same numbers with negative signs. But the point would be that the y values still get increasingly close to the number 0. So we're going to use this fact that the limit as x goes to infinity of 1 over x equals 0. And when you have any kind of function that's similar to it, 2 over x, -3 over x squared, 5 over x cubed, all of these are examples of the same kind of behavior. The larger the x gets, the smaller the y, the answer to the fraction, gets. And that's why we say the limit as x goes to infinity for all of these is 0. So keep that in your brains because you're going to need that fact. We're going to go to the handout booklets that Ms. Taz creates, and we're going to work through some of the examples. The objective is to find all the asymptotes. Now, the truth is we're not going to do it in any different way than from the way we did it back when we were in grade 12, where we have the 4 cases for horizontal asymptotes. By using these 4 cases, we can fairly quickly find all of the horizontal asymptotes and the vertical asymptotes. The part that's written at the top, that's what I did in video 1, so I'm going to skip that, and I'm going to go right to this first example, and I'm going to find all vertical and all horizontal asymptotes. I've got the cases beside, so we can use it to help us. The first thing I'm going to have to do is factor it. This factors quite easily to a product of binomials, and we can see that we have vertical asymptotes when x equals 3 and x equals -1. We can also see that we have a horizontal asymptote, again, just by using the cases, same like we did in grade 12. And so when you look at this, the degree of the numerator is 1, the degree of the denominator is 2. That neatly fits into this first case. The numerator is less than the denominator. And so we have a horizontal asymptote at y equals 0. Nothing different from last semester. The second example, the vertical asymptote is easy and quick to see. That's at x equals 5. If you compare the degrees of the numerators, they're the same. Of the numerator and the denominator, they are the same. 2x plus 4 over x minus 5. When the degrees of the numerator and the denominator are the same, you take the coefficients of the terms of highest degree, which would be 2 over 1. And so we get a horizontal asymptote, just like last semester. It's almost peer review. Now we go over to the back side of this page, and we have a case where they want us to find the equation of the asymptotes for this function. Okay, so we look at it and we go, well, the vertical asymptote must occur at x equals -2. If you look at the case to see what kind of horizontal asymptote is, you realize that this is case 4. The numerator's degree 2, the denominator degree 1. The numerator is greater than the denominator by exactly 1. That means there's an oblique asymptote. And remember, the way you find the equation of the oblique asymptote is you do a long division, which I'm going to do up here. I divide x into x squared. I expand. I subtract. 0 take away 2 is -2x. I can keep dividing here because x can go into -2x -2 times. -2 times x is -2. -2 times +2 is -4. When I subtract, -2 take away -2 is 0. But here I get a remainder of +4. The fact is the remainder is irrelevant. It's the quotient that we use. Y equals x minus 2 will be the equation of our oblique asymptote. So there's nothing new there. But what is new is if I ask you specifically to find the horizontal asymptotes, but you must do it through the process of evaluating the limit, okay? And the limit as x goes to infinity. If we look, because that's how we're supposed to get, we're not looking at verticals in these particular examples. In order to do this, I really have to expand that numerator first. So I'm going to do that on scrap paper and come up with the answer 9x squared plus 15x plus 6 over 5x squared plus 4. So really the task is you find the horizontal asymptote using limits, which means evaluate the limit as x goes to infinity. So I'm going to show you that technique, and that is the part that is new. The answer to this, if it's a numeric value, then that's where the horizontal asymptote would be. The way you do this, you're going to rely very heavily on the limit that we evaluated on the previous page. We're going to be using this definition a lot. The technique says, look at the numerator and factor out the term of highest degree, which is x squared. If I factor it out, it's kind of an unusual factoring. Factoring out really means dividing out. So you would have 15x over x squared. And then if you try to take it out of 6, you would actually be dividing it out. When you factor out x squared, also the highest down here, the first term is 5. Of course, factoring out means dividing it out. Now, what I want to do before I proceed is simplify some of these terms. And so I get the limit as x goes to infinity. The x squared over x squared actually reduces, so we don't have to write that. We're left with 9 plus, this term reduces because we have x over x squared, and so it reduces to 15 over x. This one is fully simplified. 5, these are all simplified. So now we have a series of terms in the numerator and in the denominator, and we know from the property of limits that you're allowed to evaluate the limit as x goes to infinity for each term separately, and then combine your results and you get the answer. So if I take the limit as x goes to infinity of a constant, the answer is a constant. If I take the limit as x goes to infinity of this, now we're looking at this example. Because it doesn't matter if it's a 15 on top or a 1 on top, this is going to get close to 0 as x gets very large. 6 over x squared, also that exact example, we get 0. The limit as x goes to infinity of the constant 5 is the constant 5. The limit as x goes to infinity of this term, again, this example, and we get an answer using limits of 9/5. And so because the limit as x goes to infinity of the original function is 9/5, y equals 9/5 will be the equation of our horizontal asymptote, or we to graph this function. I'm going to quickly do one last example so that you can see the technique illustrated again, but basically the strategy is to divide out the term in the numerator of highest degree. So in this case, x squared is the highest. Factoring out means dividing out, and that's how you factor it out of the numerator. When you go to the denominator, you're going to see that x cubed is the highest, so that's what you're going to factor out. If you take x cubed from this first term, you're left with 1. If you factor out x cubed, you're dividing x cubed. Now we take a minute and simplify all of our expressions. The x squared over x cubed actually reduces to have 1 over x. So I'm going to rewrite the function below so 1 over x is very clear. Then this numerator is 1 over x squared minus 4, and this denominator is 1. This reduces to 2 over x squared. This one is fully simplified. And you can almost split into 2 pieces like that just to make it a little bit easier to look at. This is the 1 over x part, and whether it's joined together or written separately, it means the same thing. Now you could do the limit for each of these pieces, so that's what I'm going to do. The limit as x goes to infinity, that is this limit. That's a 0. In the numerator, this limit is 0. The limit of a constant is a constant. The limit of a constant 1 is 1. As x goes to infinity, that middle term, the limit as x goes to infinity, sorry guys, is 0. And then we do the last term, the limit as x goes to infinity. And let me repeat that because I chopped it off and you couldn't see it. I took the limit as x goes to infinity of all of these terms. This worked out to 0. This worked out to 0. The limit of -4 is -4. And then this is a 1, this is a 0, and this is a 0. So each of these is the limits worked out separately. Of course, I don't need that anymore because I'm working it out. Shouldn't have written it. And then it works out to 0 because 0 times any product. And so y equals 0 is the equation of the horizontal asymptote for this function. And that's how you find the equation of the asymptote, by actually calculating the limit as x goes to infinity. So that's the new technique for this thing. The last thing I want to mention before you go to the homework, a lot of the questions in the textbook will give you a request after finding the vertical asymptote or finding the horizontal asymptote. It says things like conduct, sorry, you can't see that very well, but it says conduct a limit test to determine the behavior of the curve on either side of the asymptote. I crossed it out. Don't do it. Just find the vertical asymptotes. In the next one, just find the horizontal asymptotes. Don't worry about state whether the curve approaches it from above or below. You don't have to know that. Just find the asymptotes. And so the homework is at the bottom of the page as listed. And that, my friends, is the end of part 2.